ब्रॉडकास्ट का नाम किसे क्या नाम डाला है?
एक्चुअली ये तो मोने रोल इनका तो कल हो गया इनवाइटेड तो रिसेंटली अभी अशोक गुप्ता जी ये भी ऑनलाइन है ये ज्वाइन कर रहे हैं अशोक ने फोन किया है लोकान जी तो है शायद ऑनलाइन ही कह रहे थे मुझे को ऑनलाइन है उनके हो गई शायद सर उनके हो गई सर फर्स्ट सेशन में 9 से 11 वाला सेशन था ना उसमें हो गई अच्छा हो गई सर भी हाँ नवनी जहाँ दीपा लोकान दे
हेलो हेलो चेक चेक
AshokJi Gupta
हेलो चेक चेक
chair this session. Sir is a professor in the Department of Mathematics, Rajdhani College, University of Delhi. Sir has supervised, I think, five PhD students and published around 50 research papers in national and international reputed journals. Sir has around 35 years of teaching experience. Sir, I welcome you, and we are lucky enough and we are so. Thank you, sir. Now over to you, sir.
Good morning, everyone. So today, we are going to start session M2, and we have with us Professor AshokJi Gupta. Professor, are you audible? Am I audible to you? You are not audible here.
Sir, he is open. Sir, please turn on your mic.
I think you are on mute mode.
Yes. Now I am audible.
Yeah.
Okay.
Good afternoon, Professor Gupta.
Yes.
Myself, Sharma here.
Yeah. Yes.
So we are going to start with your talk. Let me introduce Professor Gupta. Dr.
Yeah.
AshokJi Gupta. He is a
Yes.
professor in the Department of Mathematical Sciences, IIT, DHU, Varanasi. His specialization is in ring theory and he has applications in coding theory and cryptography of algebra. He has earned his PhD from IIT BHU and has published several research papers in international journals, supervised PhD students. He is also in editorial board and review panel of several journals. So Professor Gupta will speak on a topic related to application of ring theory and model theory. Over to you, sir.
Okay, thank you very much. And also thank you for organizing committee, Dr. Subham Jaiswal and Dr. Sanjeev Kumar Maurya and others. That's just I will take 1 minute because I have some technical problems in my system. So I shift to another system that joined because sound is problem, I think that's. So just I am open my PPT that's okay. So request accommodation and yeah, that's how can I take that these things just so screen is visible.
No, in fact, you are visible. I think it is opposite way.
Okay, so
you have to share the screen.
so now visible.
Yeah.
Yes, it is visible.
Yeah.
Okay. So good afternoon to everyone. Because in the present technical era, that's due to this is possible that I am presenting from Varanasi. On extending modules and their generalizations, actually this is the topic from the non-commutative ring theory. So this theory that's extending module provides actually controlled decomposition structures, especially useful in non-commutative settings, where structure is more complicated. So especially many areas that this non-commutative theory extending modules helps in the many areas like structure theory of modules that provides decomposition properties, ensuring some modules fit nicely inside some sets, and characterization of rings. Many rings, right CS rings and semi-simple rings, continuous and quasi-continuous modules also That is the extending module plays fundamental role in the study of these continuous and quasi-continuous modules. Also, this connect to Bayer and Ricotta rings. That's so, and on decomposition theory. So first, actually, here our plan is the divide into our lecture plan is that introduction just and extending modules and generalization of extending modules. So actually there are many generalizations of extending modules, out of which here we present two important, that is a principally purely extending modules and purely essentially Bayer modules. That is a generalization of extending modules. So we come to that what is the history of this. The notion of extending modules come from work of von Neumann in 1930s. His interest in quantum mechanics led him to develop the theory of continuous geometry. And actually von Neumann developed the theory of continuous geometries and their realizations as their lattice of principal left ideals of von Neumann regular settings. So actually this concept comes from physics that's developed in the theory of quantum mechanics. That's so the importance of injective module in module theory is known everyone, you can say that, and more generally in algebra became obvious in 1960 and 70s. But exclusively through the impact of the publications of the lecture note of Carl Frey. When this note comes after that, the mathematician worked in the theory of non-commutative, especially injective modules and their generalizations. So an extending module here, also known as the CS module. CS module means that's complemented some modules. Is an important concept in module theory and plays significant role in non-commutative theory, as I told. So here, what the basic terminology is that's essential and cause some modules. Let A and B are some modules of an OR module. Here module, you can say that simply you can say that like a vector space or a field. Here we defined over a ring. So one property that there should not be hold here that one dot x is equal to x as like in a vector space, because our ring may not be unity, may be unity. So in general way, you can say that a vector space is a module, but module is not a vector space. So we are working in a larger domain of, you can say that, of a vector space. So here A and B are two submodules of an OR modulium, and A is said to be essential in B if A intersections is non-zero. For every non-zero submodule C of B. So in this case, B is said to be essential extension of A. Submodule N of M is called closed submodule if it has no proper essential extension in M. That is, you can say that closed is a large submodule inside M. Extending module, also known as a module is said to satisfy C1 condition, also known as extending module. Yes, CS module. So here a module is called extending or CS are said to have satisfied C1 condition if every submodule is essential in a direct subband of M, or every closed submodule is a direct subband of M. So extending module treat as a module where some modules cannot be void, you can say that. So they must sit essentially inside nice direct piece. So behavior of a submodule is a very nice. So importance of extending module is due to such modules sit between arbitrary module and injective module. So every injective module is an extending, but converse need not be true. Extending condition have proven to be an important common generalization of injective and semi-simple modules. Because a ring is semi-simple, then every module is injective. So injective means extending modules. So extending module provide a controlled decomposition structure, especially useful in non-commutative settings where structure more complicated. So C2 condition is that an R module M is set to satisfy C2 condition if any submodule M which is isomorphic to a direct summand of M is itself a direct summand of M. This condition also known as the this type of module also known as a direct injecting modules. That's a module M is set to satisfy C3 condition if direct sum of any two disjoint direct summand of M is itself a direct summand. Actually, continuous module is the set to satisfy C1n plus C2 condition, and quasi-continuous is the C1 plus C3 conditions. Here C2 implies C3, that's condition. So M injective module, what is an injective module? So an R module Q is said to be an injective module if for every submodule N, for any submodule N of M, any monomorphism phi n to M, any homomorphism phi theta n to Q, there exists a homomorphism psi m to Q such that phi followed psi is equal to theta. That's and here extension from N to M exists. That's so this is called M injective. So an R module Q is an injective if Q is M injective for every R module, and this is a quasi-injective if an R module Q is said to be quasi-injective module if Q is a Q injective. Then, so here one Newman called regular rings as a continuous, the lattice of principal left ideals is upper and lower continuous. That's so at the time that many mathematicians studied in respect of these extending modules and their generalizations, and for details you can see the monograph by S.H. Mohammed and Mr. Muller, continuous and discrete modules. That's and a book is from extending modules written by Dung, Heinz and Orbis Bauer et al. In 1994. That's so these are the literature to related to that work. Anybody can go through this book. That's so it is a well known that quasi-injective modules have C1 condition as well as C2 condition. Also C2 condition implies C3 condition. That's so continuous module, just as I told you, that satisfies C1 and C2 conditions, and quasi-continuous module is C1 and C3 conditions. That's so in general the following history is true, that injective implies quasi-injective, quasi-injective, quasi, that is a continuous module. Continuous is a quasi-continuous module, and quasi-continuous module extending modules. That's so extending module is an extension of, you can say that, injective module, quasi-injective module, continuous, quasi-continuous modules. And extending modules also can generalize purely extending module and purely essentially bare module. So purely essentially bare module introduced by my scholar Dr. Shiv Kumar, and with me that's but converse this of this implication may not be true. Here in the example, just a quasi-injective need not be injective, as R and is a, suppose Z is a ring set of integers and M is a Z n residue classes modulo M, then M is a quasi-injective R module while it is a not injective. So in fact, Zn is a fully invariant in their respective injective hulls while Zn is a not divisible Z module. So actually injective hull of a module is an extending module because injective hull of a module is an injective module. That's so continuous module need not be quasi-injective modules. Here two field K and F such that F not proper, F is a proper containing in K, that's and R is a infinite direct product of Ki. Each Ki is a K, and S is equal to generated by AI is a R. Then it is that R and S both are one Newman regular, while S is not essentially in RS. So S over S is not an injective module, which implies that SS is not quasi-injective modules. So these are examples are from the this reference that's and here some more examples that's and this extending need not be quasi-continuous. So Z module we take M, ZP direct sum ZP square. satisfied the C1 condition while it is not satisfied C3 condition. So detail if we take time, that's so that is a counter examples are here that the converse need not be true. That so this generalization is actually the proper generalization. That's so generalizations of extending modules here. Many generalizations earlier have done that. Here 1981, M. Harada and K. Oshiro introduced uniform extending module. In their literature on extending property and direct sum of uniform modules in 1981, that's uniform extending module. A module is set to uniform extending if every uniform sum module of M is essential in a direct sum of M. So there is a large condition imposed on extending module because every sum module is essential in a direct. Here is only uniform sum modules of M. So uniform module is set to uniform if all sum modules their intersection non-zero. That's so. Also in 2010, G.F. Wittmeyer and et al. That's introduced the Goldai extending modules. That's so that is also known as a G extending module. That's a module is G extending if for each sum module n of M there exists a direct summand K of M such that n intersection K is essential in both N and K. That's yani their intersection with N and K non-zero. That's any sum module of N and K. That's so that is known as G extending module. Fi extending module is introduced by again G.F. Wittmeyer and et al. That in 2002 modules in which every fully invariant in this paper. That so call a module is fully invariant extending module if every fully invariant sum module is essential in a direct sum. Fully invariant means image of a sum module again goes into the same sum module. That's so that is called the fully invariant. So it is easy to see that extending module is a phi extending while converse may not be true in general. So I am going to the main, that's our result, that's Bayer and Cauchy Bayer modules. So a module M is a phi extending and a phi k non-similar if and only if M is Cauchy Bayer. And so extending module actually want to connect to the Bayer and Cauchy Bayer modules. So I'm skipping this part. Actually main that my scholar work that's is a purely extending module actually. So in 1999, J. Clark in an article proved that on purely extending modules, that is called a module purely extending if every submodule is essential in a pure submodule. Or in other words, purely extending module, every closed submodule is a pure that. And according to P.M. Cohen, that's the submodule N of right R module M is said to be pure submodule of M if and only if this sequence is exact for every left R module L. That's. And also the condition for right R module M to be flat is that whenever this is exact for left R module N1 and N2, then if you take a tensoring from any right R module M is again exact. Then M this is called a flat. That's so purely extending module, also generalization of extending module. These two notions are equivalent over a von Neumann regular ring. Yani ki ring if you take a regular von Neumann, then extending module and purely extending module if and only if that's condition. So every extending module is a purely extending, but converse is a need not be true. If we take over von Neumann, then it is true. That's we discuss some more conditions that's over which every purely extending module when becomes extending module. That the following example shows that purely extending modules need not be extending modules. So this is a counter example. There exists a commutative continuous regular ring F such that R is equal all 2 cross 2 matrices over F that this. So this is neither left nor right continuous ring. Since F is a regular ring, so R is a regular ring. So R over R is a purely extending right R module, while R over R is not a right extending R module. So this is due to, in reference 8 proposition 14, that a regular ring is a right continuous if and only if it is a right extending ring. So R over R is neither left nor right extending R module. So we discussed when a purely extending module to be extending. So when we take a finitely generated flat R module over an Adelian ring is purely extending module if and only if it is extending module. So it means that if we take our extending module over a finitely generated flat R module, then our extending module is a purely extending. Our purely extending module is extending, because extending implies purely extending, but purely extending need not. Purely extending is a larger domain rather than extending module. So an R module over pure semi-simple ring is a purely extending if and only if it is extending, because over a semi-simple ring, every injective module is an, you can say that every module or semi-simple ring injective, so that is extending means purely extending. So that is a direct summand. So injective, so this is extending. So in general, some modules of purely extending module need not be purely extending. Here, counter example is that let R is equal Z, Z0, Z, then R is a finitely generated and Noetherian R module, which is a not extending. So therefore, R is not a purely extending R module if its injective hull over R be the injective hull of RR, then ER is a purely extending while RR is not extending that. So now we provide the condition under which the sum module of purely extending module is a purely extending. So here M be a purely extending module and N be sum module of M. If for every pure sum module P of M, N intersection P is a pure sum module of M, then N is a purely extending module. So this is the condition when sum module of purely extending is an extending module. Also let M be module, N be purely extending sum module of M and P be pure sum module of M. If P plus M, sum of P and N is a non-singular, then P intersection N is a pure sum module of M. That's. So any direct summand of purely extending module is a purely extending, and here it is routine to check that Z module ZP. This is actually the direct sum of purely extending need not be extending. So if you take that Z module ZP direct sum ZPQ is not purely extending, while ZP and ZPQ both are purely extending modules. So we discuss under what condition that the direct sum of two purely extending module is a purely extending. So here let M, this theorem states that M is we take a direct sum of Mi, of R module Mi, then the following statements are equivalent. M is purely extending, so there exists a Ij index at I is not equal to J, such that every closed sum module W of M with W intersection Mi 0 or W intersection Mj 0 is a pure sum module of M. And there is a extending exists Ij, thus that every complement of Mi or Mj in M is purely extending and pure sum module of M. So purely, essentially, we connect our extending module also the Bayer modules. That's. So Bayer modules is actually in Risby and Roman introduced the notion of Bayer modules. An R module M is said to be Bayer module if right annihilator in M of every left ideal of its endomorphism ring is a direct summand of M. So here we actually define the purely essentially Bayer module, and R module M is called purely essentially Bayer for every left ideal of IR of endomorphism ring. Right annihilator of IM is essential in a pure sum module. further R is a right purely essentially bare ring if R over R is a purely essentially bare R module. So in this proposition, we characterize bare modules as a M is a purely bare module, M is a purely extending module, M is a purely essentially bare module. So one implies third, second implies third, but this implication not reversible in general. So this is the here proof given that Z module P.G.D.A.V square and Z.P infinity are purely essentially bare module, while neither this and this are purely Z modules. And third implies, not implies second, that's key. We take M is a purely essentially bare module, but not purely bare module. That's so this is the example that is a not purely bare module. That's and direct summand of essentially purely bare module is a purely essentially bare module. This theorem characterizes the when every purely essentially bare R module is a purely bare, then every purely extending R module is a purely bare, and R is a von Neumann regular ring. So over a von Neumann regular ring, every purely extending R module is a purely bare, and every purely extending bare R module is a purely bare. So we characterize the von Neumann regular ring in terms of the endomorphism ring of the R module. That's here. That's so. Last proposition that says that for a finitely generated projective R module, then every purely essentially bare module implies that endomorphism ring of M is a purely bare ring. That's so we characterize a purely essentially bare module to purely bare ring. That's and here converse of that's when that's finitely generated Z module M is a purely essentially bare module if M is a semi-simple or torsion-free module. Torsion-free module means that's non-zero elements of cannot be annihilated by any non-zero element. Only zero element can annihilate and the module element. That's so that called the torsion-free module. That's so semi-simple or torsion-free. Then finitely generated Z module M is a purely essentially bare module. But converse of proposition need not be true in general because the M is equal Z direct from ZP be a Z module where P is a prime and N is an integer. Natural number, positive integer. Clearly M is a purely essentially bare module, but neither torsion free nor semi-simple because Z is a torsion free module. So these are the references that I have used here. That's and especially we define that this use the bare and quasi-bare modules to connect to that extending module to that purely essentially bare module. That's and also that we connected find the examples of the CS module and other things. That's so thanks for your attention. Actually, I take a time some few minutes more. That's 2 minutes because I have time up to 30. Okay.
In a short span of time, Professor Gupta has given a brief summary of generalization of module theory, starting from general module. He has come up to extending module, purely essentially bare module, torsion-free module. He has covered almost all the latest developments of generalization on module theory. So thank you, Professor. If you have any questions from the audience,
भाई दो बंदे तो हैं इसमें क्या परेशान होना
there is no question. So thank you, Professor Gupta, for your valuable talk.
Thank you very much. Thank you. Thank you. Okay. So can I exit that? Yeah, that's my still.